Imagine lying on your back in a quiet field, far away from the glow of city lights. Above you, the night sky stretches endlessly in every direction. Without the interference of artificial light, the universe finally reveals itself the way it truly is. Thousands of stars appear, scattered like glitter across a black canvas. The Milky Way stretches across the sky like a river made of ancient light, flowing silently overhead. In moments like this, something unusual happens inside the human mind. A quiet thought begins to form. It is not loud, and it is not even fully logical. It feels more like a deep instinct. The feeling that in a universe this vast, this old, and this full of stars, we cannot possibly be the only intelligent beings that exist. For many people, this thought feels natural, almost obvious. After all, there are hundreds of billions of stars in our galaxy alone. Many of those stars have planets. Statistically, it seems impossible that life would appear only once. But here is the surprising truth. That feeling, that instinct, is not built to understand the universe. Human intuition is a powerful tool, but it evolved for a very specific purpose: survival on Earth. Our instincts develop to help us find food, avoid predators, understand social signals, and navigate environments that exist on human scales. They help us judge distances we can walk, threats we can see, and decisions we can make within seconds. The universe operates on scales that are so enormous that our instincts become completely unreliable. Trying to use human intuition to understand the cosmos is like trying to weigh a continent using a bathroom scale. The tool simply was not designed for the task. And when we replace instinct with physics, mathematics, and careful observation, something unexpected happens. That comfortable assumption that intelligent life must be everywhere begins to fall apart, not because scientists want it to be that way, but because the universe itself imposes extremely strict limits. There are several fundamental realities built directly into the laws of physics. These are not opinions or pessimistic guesses. They are measurable facts about how the universe actually works, and each one makes interstellar contact dramatically more difficult than most people imagine. The first of these realities is distance. We use the word space all the time, but most people do not truly understand how vast it is. Our brains are not built to comprehend distances that large. We are comfortable with scales we experience in daily life. We understand kilometers, cities, and countries. Even the longest flights on Earth still feel manageable. For example, the distance from London to Sydney is roughly 17,000 kilometers. For a human being, that already feels enormous. It takes almost an entire day of flying to travel that far, but on the cosmic scale, that distance is essentially zero. Let's start small and build our way upward. Planet Earth itself is about 12,642 kilometers in diameter. To us, it feels massive. Entire civilizations exist across its surface, but in the context of the universe, Earth is incredibly small. If the universe were a beach, our planet would be no larger than a grain of sand. Now take one step outward. The sun sits about 150 million kilometers away from Earth. That number is already difficult to visualize. Even light, which moves faster than anything else in the universe, takes more than 8 minutes to travel that distance. Think about what that means for a moment. If the sun were to suddenly disappear right now, instantly and silently, nothing on Earth would change for 8 full minutes. The sky would still look bright. The warmth of sunlight would still touch your skin. Life would continue exactly as it is. Only after those 8 minutes passed would darkness finally arrive. That is the distance to our own star, the center of our solar system. Now let's go one step further. The closest star beyond our sun is called Proxima Centauri. It is not in another galaxy. It is not even particularly far away by cosmic standards. In fact, it is our nearest stellar neighbor. Yet Proxima Centauri sits about 4.24 light-years away. The number 4.24 sounds small, but the unit attached to it changes everything. A single light-year is the distance that light travels in 1 year, about 946 trillion kilometers. Multiply that by 4, and the distance becomes so large that the human brain simply stops trying to imagine it. So let's translate that distance into something more understandable. The fastest object humanity has ever built is NASA's Parker Solar Probe. At its peak speed, it travels around 692,000 kilometers per hour. By any normal human standard, that speed is almost unimaginable. At that velocity, you could travel from New York to Tokyo in less than a minute. But if we aimed that probe directly toward Proxima Centauri, the journey would take about 6,600 years. Think about that timeline. If a spacecraft had launched at that speed at the exact moment when workers were finishing the Great Pyramids of Giza in ancient Egypt, it would only now be reaching the nearest star, 6,500 years of continuous travel just to reach the neighbor next door. And when that spacecraft finally arrived, it might discover something disappointing, a small red dwarf star, dim and unstable, with no confirmed Earth-like planets capable of supporting life. Thousands of years of travel to reach an empty destination, and that is still only the closest star. Our galaxy, the Milky Way, stretches roughly 100,000 light years across. Crossing it at the fastest speed humans have ever achieved would take hundreds of millions of years. That is longer than the entire evolutionary history of mammals on Earth. A civilization attempting such a journey would not simply age during the trip. Over that time span, their species itself would evolve into something entirely different long before reaching the other side. And the Milky Way is only one galaxy. Astronomers estimate that the observable universe contains roughly 2 trillion galaxies. At this scale, the numbers do not just stretch human imagination, they completely break it. Distance alone forms a barrier so enormous that even the nearest stars feel practically unreachable. But distance is only the first problem, because even if a civilization somehow found the patience to travel for thousands of years, they would still face another barrier, one that cannot be solved with patience, engineering, or time, the ultimate speed limit of the universe. And that changes everything. Distance alone already makes the universe feel impossibly large, but even that enormous scale is not the greatest obstacle. The true barrier that shapes everything in the cosmos is something far more fundamental: the speed of light. Most people think of the speed of light the way people once thought about the sound barrier. For a long time, pilots believed airplanes could never fly faster than sound. It seemed impossible until technology improved and engineers eventually broke through that limit. Because of that historical example, many people assume the speed of light is similar, simply another technical barrier waiting for a future civilization to overcome. But this assumption is deeply mistaken. The speed of light is not an engineering problem. It is not a limitation of our current technology. It is a property built directly into the structure of the universe itself. Nothing with mass can reach or exceed that speed. Not because we lack powerful engines, but because the laws of physics themselves forbid it. More than a century ago, Albert Einstein showed us exactly why through his theory of relativity. What he discovered completely changed our understanding of space and time. In everyday life, the relationship between force and motion feels simple. If you push something harder, it moves faster. The stronger the push, the greater the speed. Everything seems linear and predictable. But as an object begins to approach the speed of light, physics behaves in a very different way. Instead of continuing to increase normally, the energy required to accelerate the object begins to rise dramatically. The closer the object gets to light speed, the more resistant it becomes to further acceleration. In simple terms, it starts behaving as if it is getting heavier. The faster it moves, the more energy you must add just to gain a tiny increase in speed. And the closer you get to the ultimate limit, the worse the problem becomes. Eventually, the mathematics leads to an extraordinary conclusion. To reach exactly 100% of the speed of light would require infinite energy. Not a huge amount of energy, not all the energy produced by a star. Infinite energy. That means no engine, no fuel source, and no advanced alien technology can ever push an object across that boundary. The universe simply does not allow it. Even if a civilization built a spacecraft capable of reaching 90% of the speed of light, the remaining 10% would require far more energy than the first 90. Perhaps they could reach 99% with unimaginable resources. Maybe even 99.999% if they harnessed the power of entire stars. But the final step, that last fraction, is unreachable. It is like approaching a mathematical asymptote. You can get closer and closer forever, but you will never actually touch the line. And this rule does not apply only to humans. Any intelligent civilization anywhere in the universe must obey the same laws of physics. Whether they evolved on a distant exoplanet or around another galaxy entirely, the structure of space-time remains identical. The laws of physics are universal. They do not bend for advanced civilizations. They do not grant exceptions to species that have existed for millions of years longer than we have. Every civilization, no matter how intelligent or technologically advanced, faces the same cosmic speed limit, But even if we imagine that some civilization managed to approach this limit and build spacecraft capable of traveling at extraordinary speeds, another problem immediately appears, one that has nothing to do with engines or fuel. The problem is biology. Human beings evolved under very specific conditions. Our bodies developed over millions of years to survive within a narrow range of environments. We are adapted to Earth's gravity, Earth's atmosphere, and Earth's protective magnetic field. These conditions shield us from many dangers that exist in space. Once we leave that environment, our bodies begin to struggle almost immediately. Space is not empty, it is filled with high-energy radiation, moving through the galaxy at incredible speeds. These particles, known as cosmic rays, are extremely energetic protons and atomic nuclei traveling close to the speed of light. When they strike living tissue, they can damage DNA at a molecular level. Inside Earth's atmosphere and magnetic field, most of this radiation is deflected or absorbed before it reaches the surface. But in deep space, there is far less protection. During missions to the International Space Station, astronauts already experience increased exposure to radiation. Even on relatively short missions lasting several months, scientists measure measurable increases in cancer risk, and that is only a few hundred kilometers above Earth. Imagine a journey lasting decades, centuries, or even thousands of years. Every day of that journey would expose the crew to constant radiation damage. DNA strands would break repeatedly. Cells would accumulate mutations over time. Even with heavy shielding, the risk would grow steadily, and shielding itself creates another problem. Protective materials are heavy, and in space travel, every kilogram matters. The heavier your spacecraft becomes, the more fuel you need to accelerate it. That relationship is known as the rocket equation, and it creates a brutal cycle. More shielding means more mass. More mass requires more fuel. More fuel increases mass even further. Soon the spacecraft becomes so heavy that launching it becomes nearly impossible. Radiation is only part of the challenge. In microgravity, the human body begins to change in surprising ways. Without the constant pull of gravity, bones lose density, muscles weaken, and the cardiovascular system begins to adapt to a completely different environment. Astronauts aboard the International Space Station can lose roughly 1% of their bone density per month if they do not exercise intensely every day. Muscle mass decreases. The heart, which no longer needs to pump blood against gravity, gradually becomes smaller and weaker. Fluids shift upward in the body, increasing pressure inside the skull. This pressure can distort the shape of the eyes and lead to permanent vision problems. Even after only 6 months in orbit, astronauts returning to Earth often struggle to walk normally until their bodies readjust. Now imagine a journey lasting not months but centuries. Human biology simply was not designed for that kind of existence. And even if technology somehow solved these medical problems, one more obstacle still remains, perhaps the most powerful one of all: time itself. Even if a civilization somehow solved the problems of distance, speed, and biology, one final barrier would still remain, and it might be the most powerful one of all: time. Not time as we experience it in daily life, but time on the scale of the universe itself. The universe is about 13.8 billion years old. That number is almost impossible for the human mind to fully grasp. Entire planets form, evolve, and disappear within that time span. Stars are born, burn for billions of years, and eventually collapse into white dwarfs, neutron stars, or black holes. Against this immense cosmic timeline, the history of human civilization is unbelievably small. Modern human technology, the kind capable of producing radio signals detectable from space, has existed for only about 100 years, just 1 century. That means our planet has been sending detectable signals into space for roughly 100 years in every direction. Since radio waves travel at the speed of light, our signals have only reached about 100 light years away. If we imagine this as a sphere expanding around Earth, that sphere is only about 200 light years in diameter. Now compare that to the size of our galaxy. The Milky Way galaxy is roughly 100,000 light years across. In other words, after a full century of broadcasting signals into space, humanity has barely whispered into the edge of a vast cosmic ocean. Our signals have reached only a tiny fraction of our own galaxy, and beyond that galaxy lie trillions more. But distance is not the deepest issue here. The real challenge is the timing of civilizations. Technological civilizations may not last forever. In fact, on cosmic timescales, they might exist only for extremely short periods. Think about our own situation. Humanity has been technologically advanced for perhaps 200 years. Maybe we will continue for thousands more, perhaps even tens of thousands if we are careful, wise, and fortunate. But even 10,000 years is nothing compared to 13.8 billion years. It is the blink of an eye in the life of the universe. Now imagine another intelligent civilization that evolved around a nearby star. Perhaps they developed advanced technology 1 billion years ago. They built telescopes, searched the skies, and listened for signals. But when they looked toward Earth, they found nothing, because at that time, Earth was still dominated by primitive life forms. Complex animals had barely appeared. Human beings did not exist yet. That civilization might have lasted 100,000 years, which would be an incredible achievement by our standards. But eventually their world changed, their species disappeared, or their technology faded. And their signals passed Earth millions of years before we ever built radios capable of hearing them. By the time we arrived, they were already gone. Now imagine the opposite scenario. Perhaps somewhere near our nearest star, another civilization will arise 1 billion years in the future. They will build telescopes and scan the skies looking for signs of life. But by then, humanity may be long gone. Our cities will have turned to dust, our satellites will have fallen from orbit, and whatever species replaces us may look nothing like the humans who first gazed at the stars. When those future beings listen for signals from Earth, they too may hear nothing, not because life never existed here, but because we missed each other in time. This may be the true tragedy of the universe. Not that intelligent life is rare, and not even that the distances are enormous. The real tragedy may be that civilizations appear at different moments in cosmic history. Imagine a party taking place inside a stadium the size of a planet, but every guest arrives at a different time and leaves before the next one enters. No matter how many guests attend, they will never meet. The universe may work in exactly that way. But here is where something remarkable happens when you truly accept these realities. Instead of feeling lonely, the universe begins to feel extraordinarily meaningful. Because if intelligent life is rare, then what exists here on Earth becomes incredibly valuable. The atoms in your body were forged inside ancient stars billions of years ago. Every element heavier than hydrogen was created in the violent deaths of stars long before our solar system formed. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was born in stellar explosions. In a very real sense, you are made of stardust. And through billions of years of cosmic evolution, that stardust eventually assembled itself into something extraordinary, a conscious mind capable of asking questions about the universe itself. The universe spent 13.8 billion years evolving from simple particles into galaxies, stars, planets, chemistry, life, intelligence, and finally curiosity. And that curiosity is sitting right here, watching this video, right now. That is not a small thing. That is one of the most remarkable outcomes the cosmos has ever produced. So maybe the silence of the universe does not mean we are abandoned. Maybe it means we are rare. Rare enough that the responsibility falls on us to protect this fragile experiment in awareness. No one is coming to save our planet. No advanced civilization is waiting just beyond the stars to solve our problems. The future of Earth belongs entirely to the beings who live here, us. And maybe that is exactly how it was meant to be. Because when you truly understand the scale of the universe, the fact that consciousness exists at all becomes almost miraculous. So keep asking questions, keep exploring, keep looking up at the night sky, and remember, the universe may be silent, but through us, it has finally learned how to listen. If you enjoyed this journey through the mysteries of the universe, make sure to like the video and subscribe to the channel. There are still countless questions left to explore, from black holes and dark matter to the deepest secrets of space and time. And the next discovery might completely change the way we understand reality. So subscribe, stay curious, and I will see you in the next exploration of the cosmos.